Yes, sir.
Okay, good. So let us begin today's class, which is based on the topic of CPU scheduling. So far, before your mid exam, we discussed up to chapter 5, which was on process synchronization, and we also discussed about the solutions of your quiz and mid exam questions in the previous classes. So today's topic is a significant one for this course, and I'd like all of you to pay attention to it because uh, this will cover many mathematical things without proper understanding of which you will be, let's say, in a lot of trouble in your exams. So, first of all, the basic concepts that we have already covered so far uh, falls under the criteria of the purpose of the CPU and how do we want to ensure its efficiency or optimize our usage, right? And CPU scheduling contributes to that particular uh, area of CPU utilization. And what we want to basically maximize whenever we are talking about resource optimization is we want to maximize the utilization of our resources. Then we want to be efficient while we are using those resources. And finally, we want to increase the throughput of our uh, activities. Now, what is referred to as a throughput? Can any one of you give some idea on it? Any idea? I mean, whatever you understand by this term throughput, it does. I mean, it does not actually have to be related with OS per se, but if you have any idea of the word throughput,
Sir, speed of output in a single unit of time.
good. That is exactly what correlates with operating system here as well. So what we want to, let's say we have 500 tasks, okay, and let's say in unit time our system is able to execute, let's say, 200 of them. So that's our throughput. Okay, so in a unit time, our system can handle 200 user-related or kernel-related tasks. So that basically is throughput. And the higher your system's throughput is, the more resource efficient or the more utilization it does of its resources. Okay, and what we want to minimize in terms of CPU usage is we would like to minimize how long our CPU stays idle. That means we would like our CPU or our processors to be at least busy with some relevant and important tasks. It could be user related tasks or it could be kernel oriented tasks. Okay, so we want to minimize how long the CPU basically sits idle. And finally, we'd like to minimize the process waiting time as well. And this particular terminology is of, let's say, crucial interest for this chapter, that we'd like to minimize the waiting time for all the processes in the system. By waiting time, this means it could be, let's say, how long a process waits for getting the CPU. Okay, it could be, let's say, although it's not directly termed as waiting time, but it could be that how long a process takes to complete a particular user related task or CPU related task. Okay, so before we go into that, we'd need to understand how basically the CPU and IO operations work in the uh, CPU, in the system, operating system. So the first thing is that what is referred to as a CPU burst is whenever you're doing something related to, let's say, calculation or let's say some sort of a logical operation. So CPU intensive tasks. Okay, so those CPU intensive tasks are normally covered in the CPU bursts. All right, and There is another thing which is known as an IO burst. In IO burst, what happens is that you deal with any sort of input or output instructions. So whenever a process starts, let's say this is the starting point of a process, it will start with a CPU burst. Okay, and whenever it ends, it will also end with a CPU burst. Can you tell me why?
Sir, can you repeat the question?
The question, before I repeat the question, the context was a process, whenever it starts, it will start with a CPU burst. Okay, and whenever it will also terminate with a CPU burst. But the question is, why is this the case?
Sir, what does it mean by CPU burst?
That's what I explained a while ago. It actually means that whatever CPU intensive tasks will be performed by the will be required for the process to be performed will be covered in the CPU burst. Okay, and the IO burst will cover the actions that involve input output. It could be file oriented, it could be print oriented, or it could be an input from a keyboard or mouse, whatever. So that's what are typically handled by the processor in these two unique bursts of actions. So the question was, why would a process start with CPU burst and end with the same? Well, the answer to that question is, whenever you start a process, what you necessarily do is you handle whatever previously stored information are related to that process in the memory, right? That means you load the corresponding process control block for that particular process. So it definitely is a CPU intensive task, right? So that is why a process has to start with a CPU burst. And similarly, whenever you're terminating a process, it also ends with a CPU burst because it could involve moving a process out of the job queue or moving a process out of the CPU. Okay, and the IO burst basically cannot or does not handle any of these. It only handles whatever actions you have pertaining to the IO devices in your system. So that is why the a process will always start with a CPU burst and end with the same. And in the meantime, there would be let's say different combinations of CPU and IO bursts. It could be long or it could be short bursts of different types. Okay, so that is how basically the sequence of CPU and IO bursts alter whenever a process starts execution to the point it is terminated, right? And this is what a typical CPU burst would look like. The duration could be, let's say, in milliseconds, and the frequency is typically higher at the beginning. Now, what a CPU scheduler does is basically it schedules which process will be getting the CPU, right? So there are 5 states of the process that we know of a process life cycle. So among those 5 states, whenever a process is ready, right, it will be able to enter into the CPU. Now, this part from the point of being ready or entering the job queue and then being ready for execution, these waiting times, the moment the process or the duration the processes wait in these respective queues, there are certain terminologies for that. We'll discuss them in a short while. But before that, we need to recap that CPU scheduler, as we know, can have 3 categories. The first one is the long-term scheduler, the second one is the short-term scheduler, and finally the mid-term scheduler. So what is the purpose of the long-term scheduler? It basically involves batch processing or let's say IO intensive tasks mostly. And what about the short-term scheduler? It basically deals with the CPU intensive tasks most of the time. And a midterm scheduler, what it does is ensures a balance between these two types of tasks so that user task does not only become CPU oriented or does not only become IO oriented. So a midterm scheduler is preferred over the two schedulers. Okay. Now, this process scheduling, it can be of two types. Say, for example, one process P1 gets the CPU or enters the CPU. Okay. Now, whenever, let's say, a second process will arrive while P1 is executing, preemptive scheduling, what will it do is it will allow the scheduler to interrupt the process P1 based on certain conditions. The conditions could be, let's say, the priority of the process. Okay, the condition could be based on the algorithm that you are implementing to, let's say, schedule those processes. Okay, so preemptive scheduling is, let's say, basically has the ability to interrupt a currently running program and serve or schedule a different program. And non-preemptive scheduling basically means that if a process enters into the CPU, until it finishes the execution, no other process will be introduced into the memory. So that is what the difference between preemptive scheduling and non-preemptive scheduling is. So the thing is, with preemptive scheduling, there could be certain issues, and the main concern is the race condition, as we have already discussed in our chapter 5, right? So since this is, let's say, two processes, P1 and P2, let's say P2 has higher priority and P1 is already executing. So P1 is already in the CPU, right? So what if P1 and P2, let's say, shares a common variable v? Okay, so whenever P2 arrives in the system, the scheduler will find P2 to be of higher priority. In that case, it will definitely preempt or interrupt process P1, move it out of the CPU and give the CPU to P2. But you have to be careful about this shared variable, okay, because this will lead to race conditions given that the variable values are not reflected correctly in each of these processes while the transition takes place. And we know that this transition from one process to another in the CPU is called context switching, right? So context switching, as we know, is basically what is basically an overhead, and we definitely want to minimize this type of events, right, for proper utilization and, let's say, efficiency. So you have to, let's say, structure your code in such a way that you handle these sorts of interrupts in a graceful manner so that you do not face rest condition. Okay, and that means you handle the critical section problems while scheduling these processes effectively. Okay, now whenever you have such scenarios, or whenever you want to schedule these processes, there is another entity involved which is known as the dispatcher. Okay, this dispatcher will basically, let's say, switch context or switch to user mode depending on the requirement, and to, let's say, ensure reloading or loading or storing the concurrent info of a process into its or from its process control block. Okay, so these were the basics, right, of whatever could be related to scheduling. Now, the criteria of how we measure the efficiency of a scheduling algorithm, or how we define which processes will be, let's say, given the CPU following a particular order, is judged by these metrics. Okay, so first one is CPU utilization. As I already mentioned, that we want to keep the CPU as busy as possible. Okay, then is throughput, which states, as you already mentioned, is the amount of tasks or the number of processes that are completed in unit time. So this is throughput. Okay, and the turnaround time. So these are three time related metrics that I mentioned that we'll be talking about. So the turnaround time is, let's say, whenever your process enters or gets the CPU, starting from that moment to the moment it is executed and is moved out of the CPU, is known as the turnaround time. Now, one thing might happen is that process P1, let's say, gets into the CPU at time t0. So it goes into the CPU. Now at time, let's say t1, it is swept out of the CPU, right? And finally, let's say at time t3, it is again returned to the CPU, and finally at time t4, it finishes its execution. Now the total turnaround time would be the summation of all these intervals, okay, not the time unit, the interval between t0 to t1, or t1 to t3, t3 to t4. So these will be discussed in details while we solve some mathematical examples, okay. So this basically is the turnaround time of the process. As you can see, it is written here, turnaround time is the sum of the periods, that means these intervals, spent waiting to get into memory, waiting in the ready queue, executing on the CPU, or doing IO, right? The next is waiting time. So this concept is important, that waiting time basically is defined. Let's say if I draw an example here, you have say P1, P2, and P3. Okay, so if you follow, let's say, a primitive scheduling algorithm, or let's say if you have a quantum oriented algorithm, which means that every process will be given an allocated time frame after which the next process has to be given the CPU. So let's consider that scenario, that let's say P1 will get 20 milliseconds, P2 will get 20 milliseconds, and P3 will get 20 milliseconds as well. So the thing is, when P1, let's say, arrives at the CPU, let's say it arrived at 0, okay, so in your timeline it starts from 0. So P1 arrives at time 0. However, okay, not however, let's say, and gets the CPU. So initially the waiting time of P1 is 0, because it is getting the CPU the moment it arrives. Okay. Now let's say at time 10, process P2 arrives. Now let's say that P2 is a higher priority process, and you want to you have to preempt this process P1 because it is currently executing in the CPU. So initially the waiting time for process P1 was 0. Now P1 is swapped out and P2 is given. So the next time P1, let's say it gets the CPU is at um, say for example 15. So during this time from 10 to 15, P1 was not in the CPU. Do you agree?
Yes, sir.
Okay. So if that is the case, so what is the waiting time for P1? 15
Yes.
minus 10, right? So let's say if after this P1 finished execution at time 20, so the waiting time for this process would be 5 milliseconds. Okay, so this is how we basically calculate waiting time. I'll give you a, let's say, comprehensive formula which you can use, but it is not given in the book. So it's based on how examples are solved, and it's a generic formula that will fit every scenario. And the third category is the response time. You see this value 0, the response time basically defines when the process arrives in the system and when it gets the CPU. So let's say if process P3 had arrived somewhere here, and let's say this is at time 12. Okay, so if this is the case, if process uh, P3 arrived at time 12, it gets the CPU, let's say, at 20. So P3 arrives and gets the CPU at this time duration. So during this time, P3 had to wait, right? So if we consider the waiting time, it would be 20 minus 12, which is 8 units. So the first waiting time is known as your response time. So if I look at the theoretical definitions of these three terminologies, the turnaround time states that the sum of periods spent waiting into getting into memory, waiting in the ready queue, execution on the CPU, and doing input output. And the waiting time is basically the sum of the periods spent waiting in the ready queue. And finally, the response time, which is a very a desirable metric for a certain analysis. It basically is whenever a process submits the request to get the CPU, the time difference between the submission and the first response from the CPU. Hence, the terminology is response time. So, in this particular example, as you can see, P3 submitted the request of getting CPU at this time, right? And it actually got the CPU at time unit 20. So, this difference accounts for the response time for process P3. Okay, so these are metrics, let's say, measured for individual processes in your system. Now there is another, since we have three different metrics, so considering an algorithm, if you want to, let's say, analyze whether or not it is efficient given a particular scenario, it has these three metrics: waiting time, turnaround time, and response times. However, we considered their average values. So average waiting time, average turnaround time, and average response time. So based on this, what we do is we, let's say, quantitatively analyze the performance of a particular algorithm. And what we want to do is we always want to minimize the time related factors. Okay, whereas we want to maximize the CPU utilization and throughput. Are we clear so far with these metrics?
Yes,
Sir,
sir.
can you please explain the difference between the waiting time and the response time again?
Okay, yes. The response time, if we look at the broader scale, whenever a process, let's say, let me just do one thing. Okay, so you have a process P1, okay, and what happens here is if you consider the timeline diagram, let's say a process P0 is already executing from 0, and P1, it arrives at this time tick, that is, it arrives at 5. However, it does not get the CPU immediately, right? So P0 finishes execution at 10, and that is when P1 gets the CPU. So you see, the time it arrived and the time it actually got a response from the CPU is your response time. The difference is your response time. Okay, the delta gives you the response time. Now this is part of the waiting time as well, because let's say P1 gets the CPU, executes for 5 units, and at 15 what happens is, let's say you have a higher priority process P2, right? So P1 was executing for this duration, so you have a higher priority process which arrives. So P1 will be swept out of the CPU and P2 will be given the CPU, right? And let's say P1, or sorry, P2 finishes the execution at 25 time tick, right? And that is when P1 gets the CPU back again. So during this, let's say, time period, was P1 actively inside the CPU?
No, sir.
No, it was inside the ready queue or the job queue. So this delta is not the response time, the first waiting time. So if you consider this event for P1, if you have, let's say, an array of waiting times, so the first waiting time would be, let's say, W1, the second waiting time This is W1 and this is W2, so on and so forth, right? Wn. So the waiting times for a particular process, if you take the average of it, will give you average waiting time, okay, across, let's say, n processes. Now W1, or the first instance of this waiting time, is known as your response time. And whenever you take the average of these value for all processes, will give you average response time across n processes. Now, is the concept clear?
Yes, sir. Thank you.
So, can we tell that the response time is basically a subset of the waiting time?
Yes, sir.
And in certain cases, say for example, a process has a response time, but that is the only time it waited until until finishing its completion. In that case, can we tell that it will be, let's say, a proper subset of the waiting time?
Yes, sir.
Right? So this is basically what it resembles. The waiting time is the broader category, response time is the initial waiting time. Okay, now based on this, we'll look into few algorithms, and we'll try to analyze certain aspects related to those algorithms. The first one that we have here is a scheduling algorithm, and let me let's reiterate. Scheduling algorithms can be two types. One is non-preemptive, while the other one is preemptive. Okay, and in the non-preemptive scheduling algorithms, we do not interfere with a process while it is executing. However, we interrupt a process in the preemptive class of algorithms. So the first one that you see, first come first served scheduling, is basically a non-preemptive scheduling, and this is also called as an FCFS algorithm in short. So if you consider this algorithm, you see you have three processes, right? P1, 2, 3, and you have their corresponding burst time. So the time that a process will actually require to complete is known as its burst time. And if you have a table such as this, the process list followed by its burst time, it will be explicitly mentioned that the processes arrive at, all of them arrive at time 0. Okay, and if their arrival times are different, a separate column will be given to you indicating the arrival times of each of the processes. Again, if you want to have, let's say, idea about the priority of individual processes, a separate column will be given to you as well. So the information will be provided based on whatever is asked of you to solve in your question. So don't worry about that. Just try to understand the concept here. So if we, let's say, try to resolve this particular algorithm, we'll try to see two executions. So, and then from that, we'll try to come to a decision. So you have these three processes. Okay, now let's consider two arrival orders. Let's say this is arrival order 1, and let's consider another arrival order A2, which is say for example P1, P2, and P3. Now for these two arrival orders, what we'll try to do is we'll calculate their response times, waiting times, and turnaround times. Okay, and what is mostly focused on in this domain is the average waiting time. Most of the time, you'll find me asking about the calculation of average waiting time from the question. So for the arrival order 1, if we draw the Gantt chart, by the way, this particular chart that you can see here is your process Gantt chart, or the process timeline diagram, whatever you try to call it. So every timeline diagram, for the sake of simplicity, will start with uh, 0, and the last tick on your timeline diagram will match exactly as the sum of these values. So what is the sum of these three values? 30, right? So the first tick will always be 0, and the last tick will always be the sum of the burst times of the processes given to you in the process table. And if by any, let's say, mistake, or let's say lack of attention, you find that the last tick does not correspond to the summation of the burst times of all processes, that is a pure indication of you have made a mistake somewhere in your timeline. So the first thing that you should check is, or keep in mind, is while drawing the Gantt chart of your processes, the last tick should always match the value of the summation of burst periods. Okay, so since we are dealing with arrival order 1, okay, let's deal with arrival order 2 first, so that you can understand the benefits of arrival order 1. So since this is a non-preemptive approach for the FCFS algorithm, that means whoever comes first will be served. So since P1 arrived at 0, I mean all of these three processes arrived at 0, AT indicates their arrival time. So what will we do is, we will list these processes down in the exact time location. Okay, so the values on top will indicate the arrival order of the processes. And let's say, even if we say that it arrives at 0, let's, for the sake of simplicity, we say that P1 by split millisecond has arrived at 0, P2 after P1, and P3 after P2. So we first start with P1. Or to avoid confusion, let me do one thing. Let me, I mean, it's getting overly complicated for you guys to understand. So I'll, let's say, separate their um, arrival times in this order. Okay, so P1 arrives at 0, then you have at time take 2, the process P2 arrives according to arrival order 2, and at time take, let's say, 3, you have the process P3. Okay, so you have this list, right? So whenever P1 arrives at 0, what will happen is, you will give the CPU to the process P1. Okay, and this will continue execution up to time 3. So this entire time period, P1 will be in the CPU. Now at time 3, that means when P1 finished, and remember that whenever you note down a process in this list, always write down its burst time. So P1 has a burst period of 3, so P1 goes up to time tick 3. And at this point, how many processes do we have in our system? We have the
One.
processes P2 and P3, because P1 has completed. So since you see P1 has completed, you need to keep track of it as well. So what will we do is, we will mention P1's existence here as well. However, we'll write its burst period as 0. So whenever you have a process with 0 burst period in this timeline diagram, that will indicate that process has finished execution. So in this case, you have P1 with 0, then you have P2 whose burst period is 3, and then you have P3 with burst period 24. Now among these two processes, who arrived first?
P2.
P2. So who
P2.
will get the CPU?
P2.
So P2 gets the CPU, and it will go up to
6.
6, right? So it goes up to 6. Okay, so let's take it with blue. Right now, at this time, how many processes do we have here now? We have P1 with 0, P2 with 0, and P3 with 24,
24.
right? So um, Now what will we do is we will give the CPU to P3. So as you can see here, P3 will get the CPU, right? Um, okay, just a minute. All right. So for P3, you see that it finishes execution, and at the last tick, what will happen is all of your processes will finish the corresponding execution, right? Now, um, let's try to calculate the waiting times for respective processes. Okay, so we have P1 first, then P2, and then P3. So what is the waiting time of P1? What is the waiting time for P1? 0. Why? Because it got the CPU the very moment it arrived, right? So the waiting time for P1 is 0. Since we don't have any other occurrence of P1 in the timeline, we'll keep it to 0. For P2, what is the waiting time?
So 1.
So that is correct. But one thing you have to keep in mind is we'll try to write it down as difference. So it has to be written down in this manner that the time it got the CPU. So P2 got the CPU at 3 minus the time it arrived, which is at 2. Okay, and for P3 it will be the time it got the CPU is 6 minus the time it arrived, so it will be this value. So you have 1 and 3. So if you find the average of these three values, which is 4 by 3, this will be your average waiting time. And to be safe, just write 4 by 3 units rather than mentioning milliseconds or nanoseconds. Okay, so this is the average waiting time that you have calculated for this particular algorithm, given that you follow or your processes arrive in this order. Now what if the processes arrived in a different order? Okay, so the I think I'll have to adjust this table for that bit. Now let's say your processes arrive in the order P3, P2, P1, maintaining this arrival times 0, 2, and 3. And um, the burst times for them would be, let's say, 24, 3, and 3. So as you can see, if we try to directly calculate the waiting times from this information, the things will just be reversed, right? So when P3 enters the system, we have P1, P2, P3. So the P3 will get the CPU the very moment it enters the system. So the waiting time for P3 will be 0. Now next what we have is P2, and when does it get the CPU? After P3 has completed, right? So it gets the CPU at 24, and when did it arrive? 22, right? So you have 22. The waiting period for P2 is 22 units, and for P1 it will be P1 gets the CPU after P3 finishes execution, right? So when does P3 finish execution?
30.
Sorry. When does P2 finish execution? P2
6.
finishes execution at 27,
uh,
right? P1 will get the CPU only after P2 finishes execution. So if I draw the timeline diagram, it will look something like this. You have starting with 0, you have P1 here, which goes up to 24. Then you have P2 with execution time or a CPU burst cycle of 3. It goes up to 27. and finally you have P3. Now based on this diagram, P1, oh sorry, I referred them wrong. P3, P1. Okay, so now based on this, P3 gets the CPU at the very first, so P3's waiting time is 0. P2, who arrived here at 2, gets the CPU at 24, so the difference would be 24 minus 2, which is 22. And P1, who arrived here, that's at 3, gets the CPU at 27. So the waiting time for P1 would be this time period, so which is 27 minus 3, okay, which is equals to 24. Now if you sum this, the average waiting time would be 46 by 3. Why 3? Because we have 3 processes. Now definitely the average waiting time in the arrival order 1 is greater than arrival order 2, right? Now can you, let's say, identify one shortcoming of this approach? The processes with shorter burst periods have to wait for a longer duration in the arrival order 1, okay, whereas the overall waiting time, the processes with short burst times are executed then and then, or within a very short period of time, and then the longer process starts execution with a minimal waiting time. But in this case, these processes which are very small, that means it requires very small CPU burst times, have to wait for a very long amount of time, since the algorithm is non-preemptive and P3 has a longer burst time, and thus this course results in the increase of your average waiting time. Now this effect is identified or termed as a convoy effect, which is, let's say, a drawback of the FCFS algorithm. So why is it called a convoy effect? Because if you have, let's say, a convoy, what is a convoy? A sequence of vehicles following one after the other, right? Now let's say this vehicle, if it travels slow, right, let's say its speed is very low, can these two vehicles speed up?
No.
No. But if this one has a very high speed, this will progress towards its destination, or their destination, within a very short time,
Yes.
right? So this is what is happening here. So in this case, in the arrival order 1, P1 is the first vehicle in the convoy with a very slow speed, right, or a longer burst time, and that is why the remaining 2 processes in the convoy falls behind, right, and has to wait for a longer time to progress towards completion, and this results in the average waiting time to increase. But in the other hand, we have arrival order 2, where the first 2 processes have very high speeds, and this one has a comparatively smaller speed, but still, since these 2 will, let's say, proceed towards their destination very fast, the last one will have enough time to catch up, and this results in what? To, let's say, decrease the average waiting time for the overall algorithm. Any confusion or question? No confusions? Good. So from these 2 examples, can you find out the response time for each processes? Well, you see, in this case, the waiting times for all the processes is just a single instance. That means the response time for this scenario will be equal to the waiting time,
Yes, sir.
right? As well as it will also be equal to the turnaround time,
Yes, sir.
because the time it arrived and the time it left the CPU is the time when it actually completed execution, right? So the process left the CPU only when its execution was over. So the turnaround time deals with that metric. So in this particular case, the response time, waiting time, and the turnaround time are basically similar. Now, from this particular scenario, if we want to generalize a formula for the waiting time, the average waiting time, it will look something like this. So 1 over n, where n is the number of processes in my system. Then you'll have to sum, let's say, the arrival time. Okay, yes, the arrival time, not the arrival time. Wait, first CPU acquired minus the arrival time, right? This is what we did, right? And then let's say these processes had to undergo subsequent waiting steps. So if I, where's that example? Um, just a minute. Right. So in this case, you see, if you have multiple waiting times apart from the first one, you will have to add their differences as well. So how will you let's say differentiate? You will differentiate in a way that you'll have to sum the instances where you had the time CPU released ith instance minus the time CPU given, or let's say the ith instance. So this will be for every I in the system, right? So if you take these summations for all processes and then divide it by let's say n, you'll get the average waiting time. Do you understand? Any question?
So what's the second part?
The second part basically states that, let's say you have a timeline diagram, a process, let's say P0 arrives here, goes up to this, let's say 4, and then it gets, the CPU is given to another process, let's say P1, and P0 gets the CPU back again, let's say at 7, at 10, let's say again P1 is given the CPU, and this carries on, so on and so forth. So if I try to let's say um, relate this formula with this scenario, for P0, you see the waiting time for P0 would look something like this. The time when it first acquired the CPU, when was it? 0. And when did it arrive? According to this, it arrived at 0. And given that we consider this to be a primitive algorithm, just a minute. I mean, we are talking about primitive algorithms so that you can understand the generalizability of this particular formula. So P0, it arrived at 0, got the CPU at 0. So the first the response time for P0 is 0. So that is one of the many waiting times for P0. Next, what we do is we see we consider the time difference between which P0 was not in the CPU. So this is the time duration during which P0 was not in the CPU, right? So at 4, what happened? P0 left the CPU, right? So it, okay, one thing I made a mistake is these two terminologies would be interchanged. So the time when it released the CPU was at 4, right? And when it was given again was at 7. That means we are considering this delta for P0. So when the CPU was given minus CPU released. And again, let's say P0 is given the CPU here and it goes up to 17, and then P1, let's say, finishes execution here. So for P0, you see, these are the time gaps when P0 was not in the CPU, right? So P0 finished execution at, let's say, 17, right? And P1 finished execution at, let's say, 20. So for P0, the waiting times would be summation of the response time, delta 1, which is this one, and delta 2, which is 15 minus 10, which gives you 0 plus 3 plus 5, a total of 8 units of waiting time for P0. And for P1, what we have is waiting time for P1. The, let's say, process P1 arrived at P4 time 4. So the initial response time for P1 would also be 0, 4 minus 4. Then what happened is P1 was inactive in this time frame and in this time frame, right? So what is the value of delta 1 for P1? It is 10 minus 7 because it uh, released the CPU at 7, got it back at 10. So 10 minus 7 plus, again, it released the CPU at 15 and got it back at 17. So if you sum these values, you'll get 0 plus 3 plus 2, which is 5. So these are the individual waiting times for these two processes following this particular formula. Do you agree?
Yes, sir.
So is the formula generalizable to you now?
Yes, sir.
Okay, so that is how basically you will find out the average waiting time, and the response time is basically the first part of the average waiting time formula. Okay, and the turnaround time would be the time when it actually left the CPU. You have to consider that difference as well. So we discussed about the first come first serve algorithm, where we talked about how different ordering of processes can have effect and how it can affect the waiting times for the processes and result in a very longer time for the process to complete, and which we want to minimize. And that is why most of the time, or your modern OS basically deals with, let's say, preemptive scheduling algorithms, right? And before we go into the preemptive scheduling algorithm, we'll talk about a non-preemptive scheduling algorithm, and this is basically the shortest job first algorithm, which let's say sorts the processes in, let's say, their CPU burst cycle from in an increasing order. Okay, so the shortest job first scheduling, the preemptive version and the non-preemptive version, they are, let's say, quite different. So the non-preemptive version in some cases can behave like the FCFS algorithm that we just discussed, whereas the preemptive uh, version has a different implementation technique, which we'll discuss in the next class. And I believe just discussing the SJF or the shortest job first scheduling would be enough for this class for you to understand effectively. So in the primitive version, what happens is you select processes. Whenever a process arrives in your system, at that particular moment, the processes already in your system along with the new process, you select which process has the shortest CPU burst. Okay, and then assign that shortest process with the CPU. So it might happen that a process is already executing. Let's say it has a burst cycle of 5. It has executed 3 cycles, and at time tick 3, if I draw a diagram, I think it would be beneficial for you to understand. So let's say you have P0 with, let's say, burst value of 5, at it arrives at tick 0. So at tick 3, let's say you have a process P1 whose value is 1, or burst cycle is 1. So at this time period, you have two processes in your system, right? P1 and P naught, right? Now it has already finished how many units of execution? 3 units.
Three.
So at time tick 3, P0 will have only 2 CPU cycles left, right?
Yes, sure.
Now, based on this, if you sort this, let's say, processes according to their burst cycles in an ascending order, P1 comes first, right? So at this point, P1 will be given the CPU. Now, remember, when P1 arrived in the system, P0 was preempted. That means P0 was interrupted, and then the CPU decided whether or not P0 will continue with its execution, or the new process will be given the CPU. Now, this preemption specifically tackles the drawbacks of the convoy effect. Okay, now if you look at this example here, it's, let's say, quite straightforward. In this case, what we have is we have a process, a list of processes, and their corresponding, let's say, burst periods, and we say all the processes basically arrive at 0. So in the non-preemptive version that of SJF that we're going to see is that you have these processes and their burst periods, but you will assign the CPU to the process with the smallest burst period, and that is why from this list of processes we have only given the CPU to process P1. Okay, now since this is non-preemptive and all the processes have arrived at 0, and for the sake of simplicity we consider that no more processes will be arriving soon, or will not be arriving at all. In that case, when P1 completes, what we have is P2, P3, and P4 in our system. Now, from these three processes, you will select the shorter process, or the process with the shortest burst time. And then you have P3, and this sequence goes on until all of your processes have executed. Okay, and in this case, what happens is you end up with this um, matrix for all of those processes, and you have, let's say, an average of 5.75 units of response time and 5.75 units of, let's say, waiting time. And finally, you find out the turnaround time, which is, let's say, after you calculate the waiting time, you just add one more value, the time it left the CPU. Okay, so and that will give you the turnaround time. Say for example, if you see for P1, well, someone of you I have has asked that how does the CPU know the burst period beforehand? Well, that's an intricate mechanism which we are not going to discuss in details, because it could be, let's say, defined in the process control block, or I mean, from a coding perspective, it's a complex idea. But for the sake of simplicity, we can say that it predicts, there is a formula that gives you an idea of what could be the next CPU burst cycle required for a process given its previous history. There is a formula, we'll discuss into that, but in most cases for our examples, we'll try to consider them as predefined. Okay, so uh, that's how it basically does it. Now, if we look at the primitive version of the SJF, you see, in this algorithm, we have the same processes, but their arrival times are not at the same time, right? And you have their respective burst periods. So when P0, sorry, P1 arrives at 0, it gets the CPU. Now you see these two processes, P2 and P3, which arrive at 2 and 3. Now, when you're at time tick 2, how many processes do you have in your system? P2 and P1, right? And if you consider their burst periods, P2 has a burst period of 7, and P1 as of now, I mean at time tick 2, has executed how many of its burst periods? 2 out of 3, right? So it will be left with 1. So if you sort them, you get what? You get the
P1 first. Uh,
P1 for the next cycle, right? So P1 goes into the CPU again. Now at time tick 3, what happens is P3 arrives. So you have P2, P3, and P1. Since at time tick 3 will be finished, that means P1 will be left with 0, or it will have finished its execution. So the burst period of P2 is 7, whereas that of P3 is 4. So definitely P3 will get the CPU, right? So can you identify that if we get back to our FCFS algorithm, using the arrival order 2, we saw that these shorter processes were executed as fast as possible, right, without hampering. So the shorter processes were executed to avoid the convoy effect. And in this example, as you can see, whenever a process is arriving, we are always executing the process with shorter burst period, right? So if that is the case, that means what? We are actively trying to tackle which effect? The convoy effect. You understand? The processes in this case, P1 and let's say P3 did not have to wait for P2 to complete its execution, given that, I mean, considering if it had arrived earlier than them, and if it was a non-preemptive version. So the preemption and this scheduling, or this let's say, sorry, this sorting of processes by their burst time in ascending order helps you tackle basically the convoy effect, which is a very prominent thing in the FCFS algorithm, since it does not allow for preemption. Any questions or confusion?
So, for this case,
Mm,
if a process arrives every time before P2 execution starts, then
mm.
the waiting time for P2 will increase longer and longer.
Yes, that can happen, because let's say if more processes arrive with burst periods shorter than P2, definitely those processes will be given priority in SJF, preemptive SJF. Okay, well, whereas in the non-preemptive SJF, what will happen is that it will execute as it normally does, and this will, let's say, since it is without preemption, and suppose a process arrives, and it could be the case that you have P1, P2, so with P1 burst period of 3 and P2 with a burst period of 7, and you have this timeline where let's say P1 and P2, both of them arrive at 0. So you will definitely give the process CPU to P1 first, and then let's say at time tick, sorry, not a time tick here, let me give you a different one. Let's say after P1 finishes execution at 3, P2 is given the CPU, and it will definitely carry out its execution. But in the non-preemptive version, whenever you have a process, let's say arriving at 5, P2 basically will not pay any heed to it, because it's a non-preemptive version. So P2 will finish its execution at 10, and that is when the new process, which is P3, let's say with a burst period of 4, will get the CPU. Okay, but if by this time you had more processes, let's say at time tick 7 you had P4 with burst period 2, definitely after P2 finishes execution, P4 will get the CPU, which will thereby increase the waiting time for which process? The process P3. So it can happen. You understand? So in extreme cases, the SJF may behave like the FCFS, but the non-preemptive version, the preemptive version of SJF that we saw just now in this example, will basically tackle that scenario as well. Because whenever a process arrives, all the existing processes are, let's say, taken into consideration, and their burst periods are sorted in ascending order, and the process with the smallest burst period at that point will be given the CPU, even if it involves context switching. Okay, as we know that context switching is a pure overhead, and we want to minimize it, but to avoid the convoy effect, we technically apply this preemptive SJF. Now you see, whenever we are dealing with preemptive SJF, with every process arriving, we are basically considering the remaining times for the previous processes, right? Now you see, initially in this case, the actual burst value for P1 was 3, right? So at time 2, when P2 arrived, the burst value for P1 considered was 3 minus 2, which is 1. That means what? It had only one CPU burst cycle remaining. And what we did every time is we selected the process with the shortest CPU burst, or the shortest remaining CPU burst, right? So that is why the non-preemptive version of SJF can simply be termed as SJF, whereas the preemptive version is normally termed as shortest remaining time first. So in your example, if I ask you to, let's say the terminologies can be exchanged. Say for example, if I ask you to simply implement shortest job first, it means non-preemptive. Or if I asked you to implement shortest remaining time first, it means preemptive SJF. Okay, so these terminologies are interchangeable. So pay attention while you address the problem in your questions that you'll be facing in as part of your quiz as well as your semester final exam. So yeah, basically I think I covered preemptive SJF as well. So in the next class, we'll be starting off with predictions of CPU burst cycles as well as few other algorithms for process scheduling. And as someone of you asked that how does a CPU basically know the next burst cycle? So this is how it basically deals with it. We'll talk about it in the next class, and based on uh, the previous value, it tries to guess the next value.
Present, sir.
101 স্যার।
101 মিরাজ কি মিটিং শেষ?
জি স্যার, মিটিং শেষ। আমার স্যার ফোন নেট কাজ করতেছে না, এই জন্য স্যার এটাতে জয়েন করলাম।
আচ্ছা ফাইন, সমস্যা নেই। আচ্ছা 106 108
Yes, sir.
110 111
Present, sir.
112
Yes, sir.
113
Yes, sir.
114
Present, sir.
115 116
Present, sir.
117
Yes, sir.
118 120
Present, sir.
122
Present, sir.
then 123 125
Present, sir.
126
Yes, sir.
127
Yes, sir.
আচ্ছা one thing 123 কি present না আচ্ছা 128
Yes, sir.
129 131
Present, sir.
132 134 135
Yes, sir.
136
Yes, sir.
137
Yes, sir.
139
Yes, sir.
141
Yes, sir.
143
Yes, sir.
144
Yes, sir.